Hello everyone, welcome to today's lecture on canonical correlation analysis. This is the next topic in our course on multivariate analysis. Today we're going to focus on the basics and sort of the framework for canonical correlation analysis. We do have quite a bit of theory and math to go through, so today's lecture is going to be a bit longer than usual. But in following lectures, we're going to talk about some of the specifics and some of the applications of canonical correlation analysis. Here are the objectives for this topic. So first, again, we're going to introduce canonical correlation analysis at both the population and sample level, just like we did with principal component analysis. Then we'll talk about generalizations of correlation coefficients, so the univariate correlation coefficients. And we'll discuss how CCA fits into this topic. Then I'll give a geometric interpretation of CCA, then explain the relationship between CCA and the likelihood ratio test for independence that we covered in our lectures on the tests for covariance matrices. And then finally, I'll introduce reduced rank regression and discuss how it relates to canonical correlation analysis. And so canonical correlation analysis, or CCA, is a dimension reduction method similar to PCA, but now instead of trying to reduce the dimension of one random vector, we're trying to reduce the dimension of two random vectors simultaneously. And so instead of trying to explain the overall variance or the total variance of a single vector, we're trying to explain the correlation between two vectors. And note that this is a measure of association between y and x. And so we're really trying to explain, again, the association between two random vectors. Here I have two examples of questions that you could address using CCA. So first of all, we could look at arithmetic speed and power and compare it to reading speed and power and look for the association between these two skills and see if there's any relationship. As a second example, we could look at college performance metrics and high school achievement metrics. And again, here the question would be, can we predict perhaps college performance given high school achievements? And so you can see how CCA is really looking at the association between two random vectors and try to explain this relationship. So let's start with the population model. So let y and x be p and q dimensional random vectors respectively. And so throughout we'll assume that p is less than q, so the dimension of y is less than the dimension of x. But this is done without loss of generality. We could easily just switch the notation between y and x. So let mu y mu x be the mean of y and x, and let sigma y and sigma x be the covariance matrix of y and x respectively. And so we're also going to define sigma yx as the covariance matrix between y and x. And so this is going to be the object of that we're going to focus on for this topic. Finally, we assume that sigma y and sigma x are positive definite. And so in particular, they're invertible. So coming back to sigma yx, because of the dimensions of y and x, we know it has p times q entries, corresponding to all of the individual covariances between components of y and components of x. And so the goal of CCA is to summarize this p by q matrix with p numbers instead of p times q. And these p numbers we will call the canonical correlations. And so we're doing dimension reduction. So let U be a linear combination of Y. So U is A transpose times Y. And let V be similarly a linear combination of the X's. This is a typo. And so V is B transpose times X. And so if we look at the variances and the covariances of U and V, using the properties, we can easily write the variance of U as the quadratic form A transpose sigma y A, which we know is positive as long as A is non-zero. Similarly for the variance of V, being the quadratic form B transpose sigma x times B. And then the covariance of U and V is A transpose sigma yx times B. And therefore, we can write the correlation between U and V as follows. It's going to be the ratio of the covariance divided by the square roots of the variances. And so we're looking for vectors A and B such that this ratio here is maximized, so as large as possible. And it's important to note here that we're doing this in absolute value in some way, because if we're maximizing the correlation, anytime we have a negative value for the correlation, we could just replace A or B by its negative and then turn this into a positive correlation. So we're going to look at positive correlations without loss of generality. So the first pair of canonical variates is the pair of linear combinations U1 and V1 with unit variance, such that the correlation is maximized. And then, just as we did for PCA, the kth pair of canonical variants is going to be the pair of linear combinations UK and VK with unit variance, and such that the correlation is maximized among all pairs that are uncorrelated with the previous k-1 pairs. So we're asking UK to be uncorrelated with UK-1, UK-2, etc. And VK also uncorrelated with VK-1, VK-2, etc. And when UK and VK are the kth pair of canonical variates, we say that their correlation, which we called rho k, is the kth canonical correlation. And so because we're looking for p canonical correlations, we'll get p pairs of canonical variates, where p again is the smallest dimension among the dimensions of y and x. And so next we're going to derive those canonical variates. So first we make a change of variable, and so we replace a by a tilde, where we define a tilde as the square root of sigma y times a. And similarly for b tilde, which is sigma x to the 1/2 times b. And so when we do this change of variables, we can now rewrite the correlation as follows. So now the correlation between u and v is a tilde transpose times sigma y to the negative 1/2 times sigma yx times sigma x to the negative 1/2 times beta tilde, divided by the square root of the inner products of a tilde with itself and b tilde with itself. And so if we let M be the matrix appearing in the quadratic form in the numerator, so if M is sigma y to the negative 1/2 times sigma yx times sigma x to the negative 1/2, we see this equivalence between the two maximizations. So maximizing the correlation of A transpose Y, B transpose X, this is again a typo, with respect to A and B, is equivalent to maximizing A tilde transpose times M times B tilde, where we restrain A transpose A tilde and B tilde to have unit norm. And as we will see when we prove this result, the solution to this maximization problem involves the singular value decomposition of M. Or equivalently, if you're more familiar with eigendecompositions, the singular value decomposition of M is related to the eigendecomposition of M in M transpose. Or also it's equivalent to the eigendecomposition of M transpose times M. And so here's the main result that we're going to prove in a minute. So let lambda 1 to lambda p be the eigenvalues of M transpose, and let E1 to EP be the corresponding eigenvectors with unit norm. Using the properties of symmetric matrices, we know that lambda 1 to lambda p are also the p largest eigenvalues of M transpose M. And so let F1 to Fp be the corresponding eigenvectors with unit norm. And so the main theorem says that we can get the kth pair of canonical variates as follows. So UK is going to be EK transpose times sigma y to the negative 1/2 times y. And VK is going to be FK transpose times sigma x to the negative 1/2 times x. So you can see we get the canonical variates as linear transformations that involve the eigenvectors. And moreover, we have that rho k, which is the correlation between UK and VK, is given as the square root of lambda k. And so the eigenvalues give us the correlations, or the correlation squared. So let's prove this result. First, we'll write rho 1 as this ratio that we're trying to maximize. So A tilde transpose M times B tilde over the square root of the inner products of with themselves of A tilde and B tilde. So the first thing we do is that we apply the Cauchy-Schwarz inequality to the numerator. And so if we look at what the Cauchy-Schwarz inequality says, it gives us an upper bound for the square root of the numerator. And so we see that the square root of A tilde transpose times M times B tilde is at most is less than or equal to A tilde transpose times A tilde times B tilde transpose M transpose M and B tilde. We also know that there's equality between these two quantities if A tilde and M times B tilde are collinear, or in other words, if there's a scalar C such that A tilde is equal to C times M times B tilde. And so we're going to use this result in a minute. So going back to rho 1, if we use the result we got from the Cauchy-Schwarz inequality, we see that rho 1 squared is less than or equal to A tilde transpose times A tilde times B tilde transpose M B tilde over the inner products of A tilde with itself and the inner product of B tilde with itself. And so the A tilde transpose A tilde cancel out, and we're left with B tilde transpose M B tilde over B tilde transpose times B tilde. And so this should look familiar because this is similar to what we got during our discussion of PCA and when we proved the relationship between PCA and the eigendecomposition of the covariance matrix. And so from our discussion on PCA, we know that we can maximize this ratio if we take B tilde to be the eigenvector corresponding to the largest eigenvalue, lambda 1, of M transpose times M. So we know that we can maximize the ratio using the eigendecomposition. And we know that this ratio is going to be equal to rho 1 squared if and only if A tilde is also collinear with M times B tilde. And so using this fact, we can show the following. We can show that A tilde is also an eigenvector for M transpose with the same eigenvalue lambda 1. In other words, when rho 1 squared attains its maximum, A tilde is equal to the eigenvector corresponding to the largest eigenvalue, lambda 1, of M transpose. And so both A tilde and B tilde are eigenvectors. And so the last thing we need to show is that if A tilde is equal to E1 and B tilde is equal to F1, and we go back to our original variables A and B, we see that we can express A as sigma y to the negative 1/2 times E1, and B as sigma x to the negative 1/2 times F1. And so we're done for the first canonical variates. And we can get the next canonical variance by repeating the same analysis, but by imposing an extra constraint of orthogonality, or being uncorrelated between the canonical variates. And I'm not going to go over those details, but you can look online, or you can look in textbooks to find them if you're interested. And so I've used quite a bit of vocabulary, so I just want to make sure we're on the same page. And so when I talk about canonical directions, what I mean are the linear combinations, or the coefficients of the linear combinations. And so the canonical directions would be the eigenvectors transposed times the inverse square root of the covariance matrices. And then the canonical variates themselves are those linear transformations. And so you would get the canonical variates by applying those canonical directions to both y and x. And finally, the canonical correlations are what I called rho k. And again, they're the correlations between uk and vk. And we saw that it's also equal to the square root of lambda k. So let's look at an example of how this works in practice. I'm going to define this matrix here, where I'm defining each block separately. And this is what the matrix looks like. And so you see that you get the block corresponding to sigma y is 1.4.41. The block corresponding to x is 1.2.21. And then the covariance matrix between y and x is 0.5, 0.6, 0.3, and 0.4. And so we just follow the results from the theorem. So we can use the R package expm to get the square root matrix easily. And so I'm going to define square root of y and square root of x. And then here, what I called M1 is M times M transpose. And so I define this matrix, and then I can compute its eigendecomposition, decomp1. And if I look at the results, I see that I get two eigenvalues, 0.55 and 0.001. And I also get the eigenvectors. So if I take the eigenvectors and I multiply by the inverse square root of sigma y, I get the canonical directions. And so similarly, I can look at M2, which is M transpose times M. I can compute its eigendecomposition. And then I can multiply those eigenvectors with the inverse square root of sigma x to get the canonical directions, but for x this time. And so finally, I could also look at the canonical directions and recall from the theorem, we know they're equal to the square root of the eigenvalues of either decomp1 or decomp2. And we see here that the canonical correlations are 0.74 and 0.03. So it seemed that the first canonical pair, or the first pair of canonical variates, has more correlation than the second pair. And so far we've been talking about the population model for CCA. And so in general, we will have a sample of observations from y and from x, and we want to be able to perform CCA on the sample quantities, so the sample covariances. And so just for notation, let y1 to yn and x1 to xn be random samples. So each of them are IID. And let's arrange them into n by p and n by q matrices, y and x, respectively. And note here that the sample sizes are equal. And so we would be measuring the pair yi and xi on the same experimental unit. And this is important. This is an assumption of CCA. Next, we can define the sample means and the sample covariances. And in particular, we can define SYX, which is going to be the sample equivalent of sigma YX. And so the main theorem for the population CCA can be translated to a main theorem for sample CCA. And so we can define similar quantities to M times M transpose and M transpose times M. And we can compute the eigendecomposition of these matrices to get the canonical directions and the canonical correlations. And so let's let lambda1 hat and lambda p hat be the eigenvalues of sy negative 1/2, syx, sx inverse, sxy, sy negative 1/2. And let e hat 1 to e hat p be the corresponding eigenvectors with unit norm. Just as before, the eigenvalues are also the p largest eigenvalues of the transpose M transpose times M matrix. And so we can let f hat 1 to f hat p be the corresponding eigenvectors, again, a unit norm. So the kth pair of sample canonical variates is given by these linear transformations. So we get all of the linear transformations u hat k by multiplying the matrix y by the inverse square root of sy times e hat k, and similarly for v hat k. And just as the population version of this theorem, we can get the sample canonical correlations by taking the square root of the lambda hat k's. And again, this is equal to the sample correlation of u hat k and v hat k. So let's generate some data and see how we can compute the canonical directions and the canonical variates. So we're going to use the same sigma matrix we had earlier for the population example. And then we're going to generate a matrix called YX, 100 observations, and using this covariance structure. And so from YX, so again, we're generating all 4 variables at the same time. And so we can define y as the first 2 columns of yx and x as the last 2 columns of yx. And so in base R, there's a function for computing canonical correlations. It's called canCor from the stats package. And we simply have to pass x and y, so both matrices. And if we store this into an object called dcomp, we can get the y coefficients using dcomp $y_coef. And then similarly for x, we can get the coefficients using dcomp $x_coef. And this allows us to define both u and v. So if we look at the correlation between u and v and look at the diagonal, which would be the correlations between u1, v1, and u2, v2, we get a 0.73 and 0.01. And then if we look at dcomp $core, we get the same result, which matches our expectations from the theorem 1. And recall that this is a bit different from what we got from the population correlation coefficients. The second canonical correlation was much smaller than 0.01. Next, we're going to look at how to apply canonical correlation on a real data set. The dataset we're going to use is called Olive. It's in the DS Labs package. And this dataset contains information about olive oils in Italy. So we have data on the region where it comes from, the area within those regions, and then information about the concentration in different acids. So palmitoleic, stearic, etc. And what we're going to do is see if we can find or summarize the association between the composition, so the type of acids, which we're going to store in the matrix X, and then information about the regions, which we're going to store in the matrix Y. Oops, excuse me. And so the way we define Y, so we only keep the column region, which is a factor variable, and then we use the function model.matrix, which allows us to get 3 dummy variables. And so what we get, if I go to the next slide, is that each row indicates from which region this olive oil comes from. And so, for example, we can see the first 6 observations all come from the 3rd region. And so we can do canonical correlation analysis on these 2 matrices, X and Y. Next, we're going to store the canonical variates V and the canonical variates. We're only going to look at the canonical variates with respect to X. So with respect to the acid composition. And so just as we did with PCA, we can visualize the first 2 canonical variates. And so we're going to visualize V1 against V2. We're also going to record the region from which the olive oil comes so that we can use this as a color in our plot. And so if we look at this plot here, we see how the first canonical variate is able to distinguish between northern Italy and Sardinia on the left-hand side of the graph, distinguish it from southern Italy on the right-hand side of the graph. And similarly, we can see, if we look at the y-axis, how the second canonical variate can distinguish between northern Italy and Sardinia. And so we can see how CCA was able to give us the pairs of canonical variates that we could use for perhaps classification or discrimination between the different regions. So to summarize what we've discussed so far, the main difference between CCA and multivariate linear regression is that CCA treats Y and X symmetrically. So there's no notion in general of outcome variable or a covariate. Y and X are treated the same. As with PCA, you can use CCA in the covariance matrix or the correlation matrix. So we could, for example, standardize both the X's and the Y's before doing CCA. And just as with PCA, this is equivalent to performing CCA on the correlation matrices or the standardized variables. Both approaches are equivalent. Note that sample CCA involves inverting the sample covariance matrices SY and SX. And so in particular, this means that we need to assume both P and Q are less than N. And so we have more observation than variables. Otherwise, the matrices will not be invertible. And in general, this is what drives most of the performance or lack thereof of CCA. What I mean by this is that when we have a very small sample size, this is usually when we don't get very good canonical variates, or we get very low canonical correlations. And so there may be gains in efficiency by directly estimating the inverse covariance matrices, but we won't discuss this in this lecture. Finally, when one of the 2 data sets, Y or X, represent indicator variables for categorical variables, just like we did with the Olive data set, CCA is then equivalent to what we call linear discriminant analysis. We won't talk about this. It's usually covered in the course on statistical learning, but we can see how these two dimension reduction method overlap in this particular setting.